So just a little bit of background about me. I'm the CTO and co-founder of Payy. Payy is a payments app, so think crypto Venmo, but it's for private payments. So we built, in order to achieve that, we actually had to build the phone app wallet and the network because there wasn't a private network that we could use that was in mainnet. So we deployed our first, deployed the first mainnet ZK rollup. It's a Validium rollup, so that means we just post the root hash onto Ethereum or the L1. And it's a ZK rollup, which is kind of like a play on the fact that most ZK is used for scaling and not for privacy. I think I actually stole that from Aztec, so thanks. And one of the things that's really important for us, we believe that to onboard the next billion people into crypto, you need to be using a device that the next billion people are using, and that's a mobile device. And so we worked really hard to get proof generation on the phone, and we worked on the constraints to get the proof generation on an iOS device down to 1 second. So that's just a bit of context about us, because it's kind of going to make sense throughout the talk. I'm going to kind of referencing that architecture. So as I've kind of already talked about, like, there's been a lot of use for ZK for scaling, and that's great. But we're starting to see ZK be used for privacy, which I think, that's the actual zero knowledge part. And I think the real end game is if we can actually use ZK for consensus, because then we really can have a single proof that could summarize the whole network. So what do we have today? Well, this is our architecture, but it's fairly similar to an L2, any L2 architecture that you might see, with the exception that we do all of the proofs on the client on the mobile device. So the transaction proof is sent to the sequencer. The sequencer can't see any of the details of the transactions, just that there's a proof and that it must be valid. The sequencer combines or orders the transactions, and then it sends it to the prover, and we get a proof that is sent to the L1. As I said, we're a Validium, so the proof will just be a single hash with the proof with a single hash. And then this is how it looks over time. So as I said, you have the sequencer. It's doing lots of blocks, but every so often we prove it, and then we send it to the L1. But as you can see, there's kind of a long delay between each of the rollups, and that's because it's super expensive to verify on Ethereum if we do it too frequently. And so what we want to do is we want to provide some soft finality in between rolling up to the L1. And to do that, we need consensus. So we actually implemented a consensus for our sequencer, so it's a decentralized sequencer. We actually use the hot stuff protocol for that. Now, we could have just gone the centralized route, like is quite common with rollups. But I think the industry as a whole, we need to move rollups into being a more decentralized entity for obvious reasons, that if it's not decentralized, then it's not censorship resistant. And if it's not decentralized, then if the project stops going, then the sequencer will most likely die, and the project and the protocol will die with it. But the challenge with having a decentralized sequencer is we have to provide all of these signatures to the L1, because we need to kind of prove as part of the consensus, okay, this was a sequence of transactions, that's valid, as well as this is the proof for those valid transactions. So what's the problem with sending signatures to Ethereum? Well, it's not a massive problem. No, it is a massive problem. That's the whole point of this slide. So it's expensive to verify signatures. It's about 3K gas per signature. Doesn't sound too bad, but then when you have 100 validators, that's 100 signatures. That's 300K gas. That's already more expensive than what it costs to verify a ZK proof. It limits the number of validators that you can actually have on the network, because there's a hard limit of the transaction size that you can have for Ethereum. So that now we have a hard limit on the number of validators we can have. We can never have more than, we could never get to 1 million validators. Clients have to download a lot of blocks to confirm soft finality. So as on the previous slide, I talked about the soft finality of basically between the rollups. We want to provide some finality, otherwise it would take an hour to process a transaction. But if you've got a mobile device and you're coming online, offline, then you have to download all the blocks in between when you last came online. And so we want to try and avoid that, and we want to try and give them a proof instead where they can be really up to date as quickly as possible. Oh yeah, I should probably put this at the top, but reduce security. Because we're only providing the less signatures for the last block. Obviously with consensus, if you sign the block, you're signing all previous blocks. But it would be much better if we could actually have proof of every single signature for all blocks as part of the rollup. Okay, so hopefully you agree. We want to ZK the consensus, because otherwise the rest of this talk will not work. So consensus proof requirements. So what do we actually need from our consensus proof? What do we want the ZK to do? Well, each validate will create a signature proof. That kind of already happens as part of the consensus. We need to aggregate those signatures into a single proof. Otherwise, it would be just as expensive to just send all of the ZK signatures. We need the proof size to be small. We want it to be small because, again, in a network environment, if we've got mobile devices, but just generally, network bandwidth can be a big problem if the proof sizes are large. And we also want to verify it on Ethereum, so we don't want a huge proof because then it's really tricky to do that. But the prover time can be a little bit longer because we were already proving the state transitions. Because we're a ZK rollup, that's what we do. We prove the state transitions already, so we just need to do it at the same time we're doing that process. We need to ensure that the stake for all aggregated signature proofs is more than 2/3. That's just basic consensus stuff. We need to make sure that we have 2/3 consensus. And we need to make sure that each stake is only counted once. If we're aggregating all these proofs together, the idea is to lose some information we don't need to keep around. But we don't want to lose the fact that we've already aggregated a signature in, otherwise someone could just keep adding their signature and take over the network. Okay, so the first thing we need to do is think about signature orchestration. So like, how would the actual proof construction or system work? So as I said, we've got the validators there creating their signature proofs, and then we're going to have a layer on top which is going to aggregate those signature proofs. And then you could have like n number of layers on top. In this example, I'm kind of showing we would do like 4 into 1. So we'd aggregate 4 signature proofs into one aggregation proof. But we could do that on multiple levels. So if you look at how quickly we could have a lot of proofs aggregated, if you have 4 levels, that's 256 signatures aggregated. If you have 8 levels, it's like 65K. And then for 10 levels, it would be 1 million. So we can really quickly, like 1 million signatures is kind of Ethereum level signature aggregation for just 10 levels of aggregation. This orchestration is actually probably one of the harder challenges, which is actually nothing to do with the ZK part, is like how do you actually ensure that all of these nodes, because these different aggregation proofs would be assigned to different nodes on the network. You'd need to have redundancy. You'd need to do it in a decentralized way to ensure that, that if someone decides they're not going to produce the aggregation proof, that there's a redundancy and a backup and an incentive for them to do that. But let's just assume that is in place, because otherwise this talk would be twice as long. Okay, so the signature proof, what does that look like? Well, actually, we could just do a normal signature, but we could actually do the signature proof in ZK, because one of the cool things about ZK is if you pass in a private key to a proof, you effectively just create a signature. So what we're going to do is just going to quickly witness the state hash and the stake. So the state hash would be like the root of all state of the transactions that we're looking to add to the blockchain. So if someone's sent someone some money, the state hash would change, and that's what we're trying to verify. We also need to witness the stake, because that's going to be important later when we're adding up all the stake to make sure we're over 2/3. If we take the private key, and the private key is obviously going to be putting as a private input. Oh yeah, so the blue here, that's public inputs, and the pink is private inputs into the proof. If we compute a hash of the private key, that will give us what we could deem an address that represents that private key. And then we can just constrain that address to be the same as the computed address. And then we have something that looks kind of similar to a signature. So in a traditional signature, the state hash and the stake would be the message, and then the address is basically the proof that only the person with that private key could ever create this proof, which is a signature. The really cool thing about this proof is that it's 2 to the 6 constraints, which is like nuts. That's 64 constraints to do a signature proof. And so obviously it takes like no time at all to create this proof, and the proof size is tiny. By the way, we use Halo 2 for all of our proofs. So I wrote all these proofs in Halo 2. So just bear that in mind. It'll probably make more sense on the next slide. Yeah, these are our signature proofs, and then we want to aggregate them together. I chose to aggregate 4 signature proofs together at a time. But again, because we're using Halo 2, you basically need to play around with the number of proofs that you can aggregate together, because if you were to, for example, aggregate 5 together, the time would like double. So you basically don't want to go over and need an extra advice column, or you don't want to have to add more, like a new set of constraints, because basically it's like if you go over by 1, you pay the cost of going over by a lot. Okay, so this proof is going to be a lot more complex than the other one, because we need to prove quite a few things, but ultimately we're just trying to reduce our 4 proofs into 1 proof, and update and keep track of some things along the way. So obviously, first thing we want to do is we want to verify the signature proof that we've been provided, and this is going to be for each of the proofs that we have, each of the 4 proofs. We need to verify the signature proof, and that gives us verified inputs within the ZK circuit. There's actually, within Halo 2, there's a chip. So chip in Halo 2 is basically a module. Think of it like any library, like it has like pluggable modules you can use. So there's actually one that already exists for that, which is great. So you can kind of verify a proof inside a proof. We're checking that the state hash is equal to the proof state hash, because we're going to combine those 4 state hashes into 1. So we just need to make sure that all those proofs are saying the same state hash. And then that's one way that we're reducing the amount of information that we need to keep around, right? So before we had 4 state hashes as inputs because we had 4 proofs, and now we're only going to have 1 state hash output. We need to verify the validator is in the validator set. That makes sense, right? Like, I don't want some random node just being like, hey, like, aggregate this proof for me. I'm just a random node. And to do that, we need to have some kind of Merkle tree to keep track of things, right? And that was one of the key requirements, is like, how do I keep track of who has already signed a transaction? We're going to use a sparse Merkle tree because this is my favorite type of Merkle tree, if you're allowed to have a favorite Merkle tree. I just think they're really beautiful. So don't tell, oh, this is recorded. Okay, so I'm going to give like a really quick intro into this type of Merkle tree, just because it's not as common as some of the other types of Merkle tree. So let's say I want to insert 2 into the Merkle tree. I do some binary decomposition. This is what 2 represents. Here's my Merkle tree. Where do I put this number 2 in the Merkle tree? This is a 2-bit Merkle tree. Well, what you can actually do with a sparse Merkle tree is you can use the binary decomposition to know where in the tree the node should go. So here it's going right, and then because it's a 0, it's going left. Okay, this is my location in the Merkle tree. Great. And you can also insert values that are larger than the Merkle tree. So this is a 3-bit value, but I'm trying to insert it into a 2-bit tree. Well, that's fine. Just drop the first value. This can lead to conflicts because obviously, as you can see, 2 and 6 would go into the same place in the tree. And so you just need to figure out, like, is that important to you? And we'll come back to whether that's important. But if you try and insert values larger than it is the size of the tree, then you can run into conflicts. If your tree is 160 bits, you're even if you've got a 254-bit element, so a much larger element, you're not really going to run into conflicts. Whereas if you've got a smaller tree, then you definitely are. So how do we prove inclusion in a sparse Merkle tree? Well, we take the siblings, we calculate the hashes, and bam, you have proof of inclusion. But what's really cool, again, about sparse Merkle trees, this is unique, well, not only sparse Merkle trees, but this is one of the defining characteristics of the sparse Merkle tree, is that you can prove exclusion, so I can prove something's not in the tree. And that's really important, as we'll see why in a sec. But it's basically you're just proving that that value at that slot is 0. So it's the same proof construction. And then if you want to prove insertion, well, it's a combination of proving first that it wasn't in the tree, and then proving that now it is in the tree, and so you have the old hash would have to equal the exclusion proof, and the new hash of the tree would equal the inclusion proof once you've included it. Okay, so now we know we need a sparse Merkle tree to identify whether a validator is in the validator set. That's one of the key things we wanted to do. The other key thing we want to do is we want to prevent a signature being added multiple times. And so we'll use the same Merkle tree for both of these things, because it's just more efficient to use one tree. I'm going to use a 64-bit Merkle tree. And so that is quite a small Merkle tree, but I'm not so worried about conflicts, because the validator set potentially doesn't change that often, and we can handle conflicts by just adding a nonce. So that's not a problem for us in this particular case. Each non-empty leaf holds a hash. So this is basically what does it mean to have a hash in the tree. There'd be some kind of type to differentiate between whether it's a validator hash or a nullifier hash, and then the address and the stake. So if we just put a 1 in there, then it's a validator set. If we put a 2 in there, it's a nullifier. Okay. So what I'm going to do is, so I've got the validator leaf here, creating the leaf. This is to prove that the validator is in the validator set. I'm going to do some binary decomposition, because I remember we need to do that for a sparse Merkle tree. And then we're going to calculate a root. Again, there's a chip for this available. We actually use a modified version inside of Payy, but there is one available publicly. We check that that equals the old root, and then we're good. And then we do the same thing. We're going to check that we're going to basically create a new root with a nullifier signature. So we know that if that nullifier is inserted and this new root, if we use this new root, then no one can reinsert the same one multiple times. And again, it's the same process, but we've changed the type to 2. And then this time, we're going to check that the value, the signature wasn't in the tree, and then later we're going to check it is now in the tree, and then this is the new root, and then we're going to constrain. I don't think I added this, but you would want to. Oh, I think I added it later. You would constrain the new root to be that that new root is basically the new root that we're constraining. So then we have the stake bits. We do some binary decomposition on that, because we need to check that the stake bits are less than the maximum field element, because if someone puts, usually your field element is like 254 bits, but a value could be 256 bit, and so someone can basically just hack your network by providing a bigger value than because it's modulus, it would just reset, and you could basically choose any stake value. So we have to check that the stake bits is less than the maximum field element. Less than is really hard in a SNOC circuit. You basically have to line up 2 values with each of the bits lined up, and then you go from the big endian, and you go through and you check, is this a 0 and this is 0? Okay, move to the next one. And if you hit a 1 and a 0, you know that the first value is bigger than the other value. So that's kind of how you do it. Again, we wrote a chip to do that for us. And then we want to constrain the sum. So we want to sum up all of the proof stake, and then constrain the new root that we're outputting to be the last new root that was in this for each thing. So we're basically going old root, new root, and then the new root for the last proof is the old root for the next proof. So it kind of links along. So there we have the signature aggregation proof. Yeah, so it's a little bit, there's 2 to the 21 constraints. So it's quite a big proof. In CPU, when I wrote this circuit, it took 135 seconds on my laptop. If we ran it on GPU, we could at least get it down to 30 seconds. I think we could get it down to even less than that. And the proof size is a little bit larger, but it's still within what we need. So then finally, what we want to do is a consensus proof. We want to combine all of those things together. And to do that, we need to verify these two proofs. So I haven't gone over the total stake proof, but basically we'd want to have some way to go through the validator set Merkle tree, calculate the entire stake in the network, and generate a proof. And we could reuse, as long as the validator set didn't change, we could just reuse this proof every time. And then the signature proof is the output of the aggregation proof that we just did. We're verifying the state hash, and then we're saying that the validator set root should be the old root, this is the very first root that we used. And then we want to make sure, again, like we're doing the signature stake is bigger than the 2/3 stake, so we again use the same chip for that. And then we want to verify the block proposer, which I haven't covered here. Again, like you'd want to make sure that the block proposer producing the block was actually the valid one. Again, limited time, so I didn't write a proof for that one. But we could do that. So the old proof, just to reiterate that point, like the old proof for this first, okay, it's not working. Okay, but the old proof right on the far left would be the original validator set with no signatures in it, and the far right root would be the new root. And then for the consensus proof, you would have like the old root would be the validator set, and the new root would be the new one. So this is how our rollup works today. We have the transaction proofs generated on the client. We have the execution proof, which does the state transition, and then we send that with the signatures to the EVM. So how do we add the consensus proof so we can have one proof to rule them all? Well, we take the transaction proofs. These are the same. We add the consensus proof with the new state hash. We add it to a final proof where we aggregate them all together. And then we can send that to the EVM. And we can also send that to clients because they can verify that all together. So that is one proof to rule them all. Any questions? Okay. Yeah, we use hot. Oh. I can repeat the question as well, maybe. I think the question was, which consensus do you use? So we currently use hot stuff consensus. It's basically the next iteration of like Tendermint. Nice thing about it is it has like quite a hard finality. So you can kind of be not just generating proof and then having to revert and redo all the proofs, which would be very complex. Particularly, as I said, the orchestration is one of the hardest components to this. So you want to kind of make sure that that's done correctly. At the back? Oh, anyone?
Raise your hands again.
Sorry, maybe I missed this in your presentation. I understand the validation of the stake, but whenever the committee changes, like I missed that part. Like, do you need to? Is there like drawing from a distribution to select a new committee, or like how do you change the?
How do you change the validator set?
Yeah.
Yeah. So the validator set would be a Merkle tree. So you do a very similar thing to what I just. When I showed the sparse Merkle tree, again, I didn't show it as an actual diagram, but you'd have a proof which would basically say, okay, we want to change the validator set. And again, you'd have to have some additional logic, but you'd probably do that via Ethereum, right? So you'd have like the validator, to become a validator, you would submit a transaction to Ethereum. That would have a proof of the new validator set hash. And at the same time as doing that, you would check that you received money in to cover the balance of that stake. Kind of similar to how we do the minting process right now. So when you mint money onto the platform, you basically send in USDC, and we include that in the state hash.
Sorry, but then if I want to verify your proof to rule them all, I still need to use Ethereum for some public inputs.
You'd only need Ethereum when you're adding. So just need to check the state hash or the validator set hash in Ethereum. yes.
Okay, so I still need to, every now and then I need to connect to Ethereum, pick the new validator set, and then I can use it for a stretch of time to verify your proof.
Yes, so I mean, you could do it all in ZK and not have, but we're in L2 and we borrow some of the security from Ethereum, so it makes sense for us to do that in Ethereum, but technically speaking, yes, you could write one proof that was literally just a proof and you could have it as just everything. If you had, you'd basically have to add the staking logic to part of your state logic so that like you're applying that, if that makes sense, right? Like you're applying that to it.
Thank you.
All right, let's do two more. I'll get you.
If I understand correctly, the validator set is a point to decentralization, yes?
Is a point of what?
To decentralize everything. So as large as the validator set is, this is the decentralization that I have, right?
Correct.
So what is the limitation, the upper bound, to the validator set?
How many validators could you have?
Yes.
I mean, I showed 1 million as an example. You'd need 10 phases of aggregation for 1 million validators, which would be around Ethereum level. Mm-hmm. But you could have an infinite number. There's no limit. I mean, your issue would then be like the consensus protocol would have to be able to handle that many validators. And so that's more on the like purely which consensus algorithm you use. Like hot stuff would struggle with 1 million validators. But the Casper, which Ethereum uses, does not. So again, it depends on the consensus algorithm that you use.
But the proving time will be affected too, right?
Yes, so
if I go to...
Yeah, so 10 levels of aggregation could be done in like 3 minutes. Mm-hmm. So it's not too bad.
Thank you.
All right, let's have the next speaker set up while we take the last question.
So is the proof aggregation inherently necessary for the scheme, or is it mostly because it allows you to massively parallelize? So alternatively, one way to rephrase it would be, if you had like a different proof system, right, which didn't really support aggregation of proofs that well, but had like a better end-to-end proving time for you, right? Would that, sort of like come up short? Or?
Yeah, you could just have one prover just going through and aggregating them all into one proof. You would have, the proof would be massive, so the proof size would increase. So you'd have to handle that situation, and then you wouldn't be able to parallelize it. So that would be the other issue with it. So yeah, I think those would be the challenges, but you definitely could do that.
Okay, let's thank the speaker again.